Hello students, I wanted to make a quick video about Raoult's law for volatile solutes. So we already talked about non-volatile solutes, something like salt being dissolved in water. And now we're going to be talking about volatile solutes. So the difference here is that if something is volatile, it will also produce some vapor pressure. So you can see if we look at this diagram, if we call the black dots water on the left, there's some water vapor here. That's our vapor pressure of water over the pure solvent. And then over here on the right, we might have, let's say, ethanol, and this would be our vapor pressure of ethanol above the pure solute. And when they're combined in solution, the individual vapor pressures for each of them are lowered. This is the same phenomenon we talked about with a non-volatile solute, where because there are other molecules in the mix, let's say water molecules, if we're talking about water, there's some ethanol molecules that are in the way. And so it makes it less probable that the water molecules will be able to escape the solution and become vapor. And the same thing is true for the ethanol. There are water molecules in the way that block the ethanol from reaching the surface and turning into vapor. And Raoult's law says that for an ideal liquid mixture, the total pressure depends on the composition of the liquid, the mole fraction for each substance, and the vapor pressure of each pure substance, or what it would be if you had a pure solvent or a pure solute. And in this case, an ideal solution is going to be dilute, and there are similar intermolecular forces for both solute and solvent. So for example, where we had ethanol and water, that's a good example of an ideal solution or something that should follow Raoult's law. Because the intermolecular forces are comparable, both solutions make hydrogen bonds. The equation for this just shows the mole fraction, which is represented by chi, times the original vapor pressure of the pure substance. So if this were for water and ethanol, this would be the mole fraction of water times the vapor pressure of water when it's all by itself. And then this could be the mole fraction of ethanol plus the vapor pressure of ethanol when it's all by itself. And I've added on a third one. This could go on for as many solvents and solutes as you mix together. Usually it's just two in the problems that we're going to deal with, but you could have a third and even more than that. So that's why there's kind of trails off over here. But usually just two solutions or two substances that are mixed together in solution. So if we look at these mixtures, in the first one we have acetone and ethanol, in the second one we have pentane and hexane, in the third one we have methanol and water. And the question is, which would be least likely to follow Raoult's law? And if we look at them, on the right we've got water and methanol. They both make hydrogen bonds, so those are likely to be similar intermolecular forces. In the middle we've got pentane and hexane. Those are both going to have London dispersion forces, and they're about the same size, so it's likely that they would have similar intermolecular forces. And on the left, we've got acetone, which is polar, so it can have dipole-dipole forces, and ethanol, which also makes hydrogen bonds. So acetone and ethanol are the least likely to follow Raoult's law because there is a difference in the strength of the intermolecular forces comparing solute-solute interactions with solute-solvent interactions. So go ahead and pause the video and see if you can solve this problem on your own. This is a practice problem with Raoult's law. So again, we have the vapor pressure of pure benzene, 95.1 millimeters of mercury, and the vapor pressure of pure toluene is 28.4 millimeters of mercury, both at 25 degrees. So the question asks, what are the partial pressures of benzene and toluene in a solution in which the mole fraction of benzene is 0.6? So because we know the mole fraction of benzene, we also know the mole fraction of toluene. They always add up to 1. So the mole fraction of toluene will be 0.4. And we can find the partial pressures of each one just by multiplying the mole fraction times the original vapor pressure. So we can take our 0.6 for benzene and multiply by 95.1, which is our vapor pressure of pure benzene, and that gives us 57.1 millimeters of mercury. And likewise for toluene, we take our 0.4, our mole fraction, and we multiply by 28.4, which is the vapor pressure of the pure liquid. And that gives us 11.4 millimeters of mercury. And the total vapor pressure is just the sum of the partial pressures of each of those. So if we add them together, we should get 68.5 millimeters of mercury. So we can go ahead and talk through this problem. So this is a mixture of hexane and octane mixed together. So we have 8.62 grams of hexane and 22.8 grams of octane. And we have the vapor pressures of the pure liquids up at the top. So first things, we want to turn the grams that we have into moles because we need the mole fraction of each. And for hexane, we get 0.1 moles, and for octane, we get 0.2 moles. So our total moles is 0.3, and we'd have 1/3 would be our mole fraction for hexane, and 2/3 is our mole fraction for octane. So if we substitute that in, 1/3 for hexane times the vapor pressure of hexane, so that's our chi for hexane is 1/3 times the original vapor pressure of hexane, plus 2/3, which is our chi for octane, times the original vapor pressure of octane. And we add those together, we get 58.7 torr. So finally, take a minute to write down for yourself why vapor pressure is lowered when a solute is dissolved in a solution, and compare and contrast the vapor pressure lowering for volatile and non-volatile solutes. To summarize here, vapor pressure will be lower because it's less probable for molecules within the solution to be able to hit the surface and become vapor. But the probability of a molecule in the gas phase hitting the surface is about the same. So you end up having an imbalance there. It's not at equilibrium because the condensation is greater than the evaporation. So to get to equilibrium again, it ends up that a smaller amount of vapor pressure will be produced. And the vapor pressure is always determined when the system is at equilibrium. The process of vapor pressure lowering is similar for volatile and non-volatile solutes because the vapor pressure of the solvent will be lower in both cases. But for a non-volatile solute, it doesn't produce any vapor pressure of its own. A volatile solute does produce vapor pressure, and because it's in the mixture, the vapor pressure for the solute will also be lowered. So Raoult's law for volatile solutes, you have to take into account the vapor pressure of both the solute and the solvent, so you add those together.